Hello, this is Dave at devplays.net. Today we're presenting part 2 of our Minecraft integrated circuits tutorial. This part is all going to be about RedPower and all the nice new stuff you get with that mod. Then part 3 will cover the integrated circuits mod itself. Okay, so let's go in and see what we got. Okay, there we go. So the first thing we need to understand about RedPower is that it's a mod that gives you a lot of nice new things and advances the concept of redstone with wires, lamps, all kinds of integrated circuits, and just makes everything much more smaller and compact and easier to use. Now the first thing is, with RedPower, you can transmit a signal up to 255 blocks in length. Traditional redstone, you can only do 15 blocks and then you need to put a repeater in. As you can see here, I've got 15 blocks, then a repeater, then 15 blocks again, then another repeater. Now the disadvantage with this is that each of these repeaters adds a small time delay onto the transmission of a signal. I can best demonstrate this if we go into night mode. Okay, now this here is a redstone repeater that's 128 blocks in length. So it's 8 sets of 15 redstone and then 8 sets of repeaters. Now when we flip the switch, there's going to be a delay before the lamp lights up at the far end. Each redstone repeater adds about 1/20th of a second. So we've got 8 redstone repeaters, so it should be about 1.6 seconds from flipping the switch to seeing the lamp light at the far end. I'll just show you that again. So it goes boom, 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 and then the light at the far end showing you that the circuit's complete. Now let's compare this to redstone wire, which is the same. It's 128 blocks in length. There's no repeaters needed, and as you can see, when I flip the switch, the light comes on almost instantaneously, which is a huge advantage when you're making circuit designs, because you don't need to worry quite so much about timing issues and distance issues. Okay, so that's the basics of redstone wire. Now redstone wire comes in 16 colours. These are insulated, which means you can lay them next to each other without any block spacing between them. 16 colours. The traditional numbering system is white is 0, orange is 1, all the way up to the far end when you've got red at 15 and black at 16. So you've got the capability there to do 16 signal lines all parallel to each other, different colours, and those will transmit 16 signals. Now if you compare this with a traditional Mindstone computer where you were using redstone, each signal line you need to put a space between it, mount it on blocks, and so to get 16 signal lines you would need 31 blocks in width. That's a hell of a space problem. Now we have this thing here called bundled wire, which is basically a collection of all 16 coloured wires from before, but in a single bundle. Now you can take taps off this for each individual colour, but it will transmit all 16 signals through a single wire. So you've got this bundle wire takes up 1 space, and the same thing in traditional redstone would take up 31 blocks. So it's again a big saving. So let's just see how this works in practice. Here's a bundled cable, and we're going to join all these individually coloured wires together. Okay, those are all joined, and then we're going to get something from the Project Red called a bus input panel, and we'll just put this on the far end. Now a bus input panel is basically 16 switches that correspond to 16 wire colours. So if I flip switch 0, which is the white one, you can see that the white lamp at the far end is lighting up. If I flip switch 15 here, you can see that the black lamp is lighting up, and so on. So that's a very simple way of transmitting the signals through a bundle cable and then taking a tap off with the appropriate colour. Now bundle cable also comes with its own colour coding system as well. The traditional bundle cable, if you lay it side by side with each other, it will join together. As you can see here, you see that he's joining himself together wherever he needs to meet. Now we also have the coloured bundle cables. Let me just get, say, a white bundle cable and an orange bundle cable. They're all the same, they all contain the same 16 signal lines, but the advantage of these is that you can lay them parallel to each other and they won't intersect. So again, that saves an awful lot of space when you're doing layouts and designs. Right, so let's just take a look at the other stuff we get in Redstone. From the top, you've got Redstone Core, which contains various bits and pieces, illuminars, routing chips, various bits and pieces that we probably won't use. You've got the transmission, which is the red alloy wire and then all insulated coloured wires. The bundle cables, again in 16 colours. The framed wires in 16 colours again, and a bundled frame, which allows you to do vertical designs. You can run things up vertically without the need to blocks to tie things to. Oh yeah, before I forget, another advantage of the wire is that you can run it up and down the sides of blocks. So if I just put a block here and then run some wire, you'll see that I can join to the side, go over the top, come down the other side. It will follow the contours of whatever you're laying it on. You can also run it like this, and it will just automatically join wherever it's, using an intelligent kind of system to join to the same color. Okay, so that's Redstone transmission. You've got Redstone transportation, which again we don't really use. Redstone exploration, which is again something we don't use, but it's just, there's a few coloured pouches, a few seeds, a few new sets of armour and weapons and things that have nice bonuses to them. Example is green sword, plus 6.75 attack damage, peridot sword. This here be the Redstone integrated circuits. This is the nice bit because this gives you all your basic gates, gives you some various other integrated circuits such as latches, flip-flops. You've got your bus input panel, you've got 7-segment displays. There's a lot of nice stuff there. Now if we just take a look at the traditional way in Redstone of doing logic gates. For example, this is a NOT gate, and it always involves the same kind of thing. You've got blocks, you've got switches, you've got torches, you've got redstone. So this is a NOT gate. So when we flip the switch, the light goes out. When the switch is enabled, it goes out. So that's just a basic 0-1 NOT gate. This, for example, is an AND gate, which has got 2 switches, and you need to flip both of them to get the output signal as a 1. Likewise with an OR gate. These are all pretty standard designs that you've probably used 1,000 times before. NAND gate, NOR gate, all of those take up about 4 or 5 blocks. The more complex ones, for example XOR, that one takes up a huge area. Now if we look at the RedPower Equivalents, you'll see that each logic gate takes up exactly 1 block. So here you've got the NOT gate, again similar thing. You've got the AND gate, and you have to flip both switches to get the 1 signal out there. Now these gates are configurable. When you first put them down, the output will usually be facing away from you on the far side, and then you've got up to 3 inputs. Now you can use your screwdriver to configure these exactly how you want. Let me just find the screwdriver. I appear to have lost it. Okay, there's a screwdriver. So when you have your screwdriver highlighted, simply right clicking will rotate the gate to whatever orientation you want. And then when you hold down the shift key, you can select which inputs you want to the gate. Enabled. This one here is all 3 inputs enabled. A couple of right clicks again. Here it's just for left and right input enabled, and the one at the back is disabled. So it's just a simple 2 input gate. And then you can even go to 1 input enabled. I'm not sure what that means in context of an AND gate. It probably just works the same as a buffer. But anyway, this is completely configurable exactly how you like, just by holding shift and right clicking with your screwdriver. So as you can see, all the basic gates are there. They all take 1 block. You've got NOT, AND, OR, NAND, NOR, XOR and XNOR. And as you can see, those 1 block components are a hell of a lot easier to use than, say, this 20 block component to do the same thing. So now we've had a look at that, let's go and put a few of these things together and make ourselves a 7-segment display. Let me just fly over here for a minute. Right, so what we've got here, we've got some bundle cable, which allows us 16 signal lines. Here we're using some frame bundle cable to take the design off the ground. Here we're using some framed coloured cables to run it up the way, and then we've got some lamps there and some obsidian just to make it look nice. Okay, so now the display's blank. So if I switch on the segments, I'll get it eventually, just bear with me a minute. See, when you've got your screwdriver highlighted, it'll rotate things. So you have to unselect the screwdriver, select something else down here, and then you can click on the individual buttons on the bus input panel. So we'll switch on segment A, segment B, segment C, D, E, F and G. We don't, on this design I don't have any decimal points, so the last bit isn't used. And then here again for the high digit, segment A, B, C, D, E, F and G. So now we're showing 88. Okay, let's just switch all those off for a minute. So as you can see, that's again, doing this 7-segment display is obviously a lot more compact than if you did it with traditional redstone and blocks and pistons. Right, and then the next thing we're going to look at is a really complex design. This one is basically a 8 digits binary to hex display component. The basic parts of this, you've got your input up here, where you get your 8 input signal lines. First four lines are going to be for the low digit binary. Next 4 lines are going to be for the high digit binary. Then it comes down here, and this is just splitting them off into 2 sets, so that the low digits processed on the left hand side, and the high digits processed on the right hand side. And then we're just using NOT and buffer gates here just to invert the inputs. So for each of the 4 input lines we convert it into 8 signals. I've just put some lamps there to show what's going on. So as you can see now, this is binary 0000 selected, and the 4 lamps that are lit are the inverses, so it's 1111. Then over here we're using a combination of null cells and AND cells, so that depending on which combination of the signal lines are selected, it will select one of the 16 outputs. So that's basically 4-digit binary to 16 line decimal display. If I just go over to the bus input panel, I'll just flick on the first 4 lines, and now you can see that line 15 is selected. Okay, let's just go back and switch that off again. So that's the basic logic for converting 4-digit binary into 16 input lines. Then those 16 input lines come down to the bottom, and then again here we've got another patch panel, this one using buffer gates and null cells, which depending on which of the 16 input lines are selected, it will select the appropriate segments for the display. So here this is binary 0, so you're actually selecting segments A, B, C, D, E and F, and segment G isn't selected. And likewise on the high digits you can see the same things happening there. So if I just connect the I'll just connect the output of this integrated circuit to my 7-segment display. I've got a bus input panel up here which is feeding across to the input. So now as you can see, when the input is all zeros, the 7-segment display is showing 00. Now bear in mind this is a binary converter now, so when I click on binary 1, you can see it's gone 0, 1. When I select all 4 of them on the low lines, that's hex digit F, which is equivalent to binary 1111. And then for the high digit, same thing, 1, 3, 7 and F. So you've got a complete integrated circuit there. Use solely the redstone components. Now, while this might look like quite a big design, and you may have done it in other ways with traditional redstone, bear in mind that this design is basically only 1 block high. Traditional redstone designs, you might end up going, I don't know, 20, 30 blocks high. It really depends on the complexity of a design. But here you can see everything that's going on. It's all laid out flat on a linear plane. Now, this circuit itself is 64 blocks by 64 blocks. And in our next episode, we're going to see how we can take this design and compress it down to a single block only using the Integrated Circuits mod. Okay, so that's everything for today. The save game for this world you can find on the website. You'll find a link to the website in the comments. I hope you enjoyed the video. Drop me a like, subscribe. Take care. I'll see you next time.